Hello, students. We are here to discuss what I call the basics of differential equations, which involves some terminology, verifying solutions, and then, well, this is a topic we will pursue more in the next video or two. First question, well, what is a differential equation? Well, this is an equation, first and foremost. And this involves, I will put this an unknown part in parentheses, but we have some unknown function and one or more of its derivatives. Now, a solution to a differential equation, well, this is a function. Say we have y is some function of x that satisfies the equation. Now, the good news is we know how to solve some differential equations already. In particular, say we want to find all solutions to this differential equation. dy dx is 1/2 plus the sine of x. The rate of change of y with respect to x is given. Well, we can integrate here. So we will have y is the integral of 1/2 plus the sine of x dx. We have 1/2 x, and then when you integrate sine, we get negative cosine, so minus cosine x plus c. Okay, so this is it. This is our answer. Now, just like when we first started learning how to integrate, certainly in this example, and generally with differential equations, you can check that the solution works. And how would you do this? Well, we can calculate d dx, and I will even include the plus c if I would like. It's fine. And the derivative of 1/2 x is 1/2. The derivative of cosine is minus sine, but with this negative in front, we will get plus sine. And the derivative of the constant is 0. So, in fact, this function satisfies the differential equation in all solutions. And this is my remark here. This is what's called a general solution. Typically, general solutions have some constant c in them. And well, for every single constant c, we have a different solution to the differential equation. Now, next example, you notice this is the same. dy dx is 1/2 plus sine x. Same differential equation, but I want the solution that passes through the point 0, 5. So first of all, let me just copy my general solution and paste. Now, evaluate at 0. Y of 0, well, this is 1/2 times 0 minus the cosine of 0 plus c. And we want this to equal to 5. Well, the cosine of 0 is 0 is here. Think about unit circle. Cosine of 0 is 1. So I can rewrite this as minus 1 plus c equals 5. And I get that my constant is 6. And so my answer, I'll write it over here. We have y of x is 1/2 x minus cosine x plus 6. This is the solution to this differential equation that passes through the point 0, 5. Now, more terminology here. This is what's called a particular solution to the differential equation. Now, here's another example, and we see in this example some more important terminology. Maybe I'll make this pink. Solve the initial value problem. What does this even mean? Well, we have some differential equation, and we have this initial condition, and we will have a particular solution here. Okay, let's go. This is one kind of like the last. I can write dy dx just as a function of x, so that when I solve, I just integrate. Dy dx is 6 minus 2x plus 1 cubed. Now integrate to get a general solution. I get 6x minus, well, technically this part would be chain rule, but you notice my inside function has derivative 1. So I'm just going to integrate. We have 2. We add a power and then divide by the higher power plus c. Okay, this is my function y. Now, maybe in the next step, I'll simplify this to be just 1/2. So now let's use our initial condition. Y of 0 is 3. Y of 0 would be 6 times 0 minus 1/2 times 1 to the 4th plus c. And I want this to equal 3. We solve for the constant c. Well, you see I get minus 1/2 plus c is 6/2. And then we can solve. C is 7/2. Now, I'm ready to write my final answer. Y of x, this is 6x minus 1/2 x plus 1 to the 4th plus 7/2. And if you wanted to, you could certainly take the derivative and see that it satisfies this differential equation. You could also evaluate at 0 and you will get 3. So it satisfies the initial condition. Okay, wonderful. Here's another example. Now, we want to show that this y is a solution to this differential equation. This is the first time we've seen a differential equation that is not just dy dx or y prime is some function of x. Here we have y prime plus y equals 2 plus x squared. Well, how can we do this? Let's see. We can start with the left-hand side. What is y prime plus y? We should be able to simplify and arrive at the right-hand side of the differential equation. Okay, let's differentiate. You notice this is just quadratic. So when we differentiate, I have minus 2 plus 2x. Now add y. Y is 4 minus 2x plus x squared. 4 minus 2x plus x squared. Okay. I have minus 2 plus 4. This is 2. I have 2x minus 2x. This adds to 0. And then I'm left with just this, x squared. Okay, what have we shown? For this function y prime plus y equals 2 plus x squared. We're finished. Maybe I'll put a check mark. Very nice. Next, we have a definition, the order of a differential equation. This is important terminology here. The order, well, it's the highest order derivative appearing in the differential equation. So if we go back to the 3 examples we've seen so far, dy dx is 1/2 plus sine x, dy dx plus 2x plus 1 cubed equals 6, and then y prime plus y is 2 plus x squared. Well, you notice looking at these that all 3, these are all first order differential equations. And it's definitely the case that the first order differential equations are the ones we will focus on in this course. Okay, now here is just some nice practice verifying solutions. So we have two different differential equations, 1 and 2. For each one, I'm giving you two possible solutions, and we're determining which one is and which one is not a solution. Okay, also note that both are first order. Maybe I will put this as a remark. Both 1 and 2 are first order. This is this new terminology. You'll notice on this differential equation, I have a y prime squared and 1 minus y squared. Okay, so let's take y prime squared and y prime squared. For the first one, well, when we differentiate cosine pi x, this is chain rule. We take derivative of the outside, evaluated at the inside times derivative of the inside function. Okay, for the second one, sine x, this is not chain rule, we just take the derivative. We have cosine x. Well, let's simplify this top one. We have pi squared, sine squared of pi x, and this one is just cosine squared. On the other hand, maybe, let's move this down just slightly. 1 minus y squared is what? Well, we have 1 minus cosine squared pi x. And here, 1 minus y squared is 1 minus sine squared x. If you stare at these, I'm trying to see, is this equal to this? Or is this equal to this? You might think the answer is no and no, but we have a trig identity. What's the most important trig identity there is? Well, it's that sine squared theta plus cosine squared theta equals 1. So here, if we just subtract sine squared from both sides, we get cosine squared is 1 minus sine squared. So this is equal to 1 minus sine squared, which is 1 minus y squared. It seems we have found our answer, that our answer is letter B. Let me highlight this now. However, let's just make sure that A does not work. So, what is 1 minus cosine squared pi x? Well, if we use this most important trig identity, what would it be equal? Just sine squared pi x. Now compare that to what we have above. Sine squared pi x is not equal to pi squared sine squared pi x. And so this will not be 1 minus y squared. Okay, so B is our answer here. We have verified. Number 2. Well, the differential equation says y prime over x equals 1 over y. So maybe I should write these as powers. This is a 1/2 power, and similarly, so is this one. Let's start with the left-hand side. If I have y prime over x for the first one, well, 1/2 power, 1/2, okay? And then the power minus 1 is negative 1/2. I'm going to go ahead and write that in the denominator as a square root. So we have a 1/2. In the denominator, I have a square root, but don't forget this is chain rule. So I put in my inside function and then times derivative of the inside function, which is 2x. Well, so far that's just y prime. You see, I have this over x. So this will go down here. What do I get here? I have an x over x. I have a 2 over 2. So altogether, I just have 1 over the square root of x squared plus 3. And you notice this equals 1 over y. So, well, we've already found our answer. It's letter A. But let's go ahead and verify that B does not work here. Once again, we can start with y prime over x. We have 1/2. Just as I did before, I will go ahead and put the minus 1/2 power as a square root in the denominator. So here's y prime. Now, we're dividing by x, so it goes down here. And you notice this is 1 over, we have 2x to the 3/2. And this is certainly not 1 over y. So we have answered both 1 and 2 here. All right, there's more examples, very much like what we just did, except here we have 4 differential equations and we have 4 different solutions. So every solution will match with exactly 1 differential equation. The other thing to notice here is that all 4 of these are second order. We have y double prime, y double prime, y double prime, and y double prime. So let's write that remark. These are second order differential equations. There are first examples of second order differential equations. So how are we going to go about this? Well, perhaps I can just start with the solutions and start by calculating the second derivative, because all 4 of these equations involve the second derivative. So on A, we can calculate the second derivative. Well, the first derivative, you see this is chain rule, so we have 2e to the 2x. Second derivative, we differentiate again. We have 4e to the 2x. You might see the equation that works already, but I will go ahead and calculate the second derivatives for all 4 solutions. So for B, y prime is 2x, and y double prime is 2. Letter C. Y prime is 1 over x, derivative of natural log is 1 over x, and y double prime, well, you see this is x to the minus 1, so we would have minus x to the minus 2, or minus 1 over x squared. Letter D, derivative of cosine is minus sine. And differentiate again, we have minus cosine. Okay, now we have all of the second derivatives calculated. Let me make this slightly smaller and we will match the differential equations. Immediately, I see something with this very last one. You see, the second derivative is negative the function, and that's really what this is saying. So for D, the letter that will match is letter I, because y double prime plus y, this is minus cosine x plus cosine x, which is 0. So we have our first one. Now I don't need to worry about letter I anymore. Now we continue. This is kind of detective work, searching for patterns here. So what do I want to try next? Okay, let's do number 4, which I see here. Look at y double prime and look at y prime. And we see exactly number 4. So number 4 says x, y double prime plus y prime equals 0. And let's verify that in this case. Xy double prime is minus x over x squared plus y prime. You see, this is minus 1 over x plus 1 over x, which is 0. Very nice. So number 4 corresponds to letter C. Okay, now we have 2 left. We have 2 and 3. All right, I see 2 here. This is a fun problem, but definitely takes some thought. Well, in 2, we need y double prime minus y prime minus 2y, and this should equal 0. Y double prime, you see, is 4 e to the 2x. Oh, y prime is 2 e to the 2x. 2y is 2 e to the 2x. You see, we have 4 e to the 2x minus 4 e to the 2x, which is 0. So this is wonderful. We have found that 2 has solution letter A. The last one is letter 3, and I can go ahead and put that here. Must be. But I think it's easier to work with if I move everything to one side. So let's do that. You notice letter 3 says y double prime plus x y prime minus 2y is 0. And let's verify that. Y double prime plus x y prime minus 2y is, y double prime is 2, x y prime is 2x squared, and now subtract off 2 times x squared plus 1. Okay, how wonderful is this? This was the one I saved for the end because it wasn't so obvious. But now we see we have 2 minus 2. We have 2x squared minus 2x squared. Altogether, this gives us 0. And so we have verified. This kind of problem is a bit tricky at first, but the more you practice, the more you get a sense of working with differential equations, verifying solutions. Okay, here are 2 last examples for this lesson. And this first one, well, we have an initial value problem, and y prime, or dy dx, is a function of x, and so we can integrate. But I like this example because we must use substitution. So first of all, we can integrate. We have the integral of x e to the x squared dx. This would be something we could solve, well, last week, say, when we were doing indefinite integrals. All right, how do we integrate this? Well, u is x squared du 2x dx. Now, handed to me in my integral is not 2x dx. We have x dx. And this is 1/2 du. Let me put this in a box. We have e to the u times 1/2 du. Now let's integrate. Well, we integrate e to the u, we have e to the u. Finally, we go back to x. So we have 1/2 e to the x squared plus c. Now this is the general solution, or if you're thinking about integration, it's all antiderivatives of x e to the x squared. We're looking for a particular solution, and so y of 0 is 1/2 e to the 0 plus c. Well, we want this to equal 0. Okay, you see, e to the 0 is just 1, so we have 1/2 plus c equals 0. Now we see the answer. My constant is -1/2. Okay, I'm ready for my final answer here. Y of x is 1/2 e to the x squared minus 1/2. This was a great example because, well, we got to practice substitution. Now, here is my last question. Okay, this is not y prime is some function of x. Then we would just integrate. But I'm asking, what is the general solution to the differential equation y prime equals y? Now, we will study this more in the next section, this type of differential equation. So think about it for a moment. What is this saying? It's saying a function's derivative equals itself. The derivative equals itself. Now, what function is the only function you know whose derivative equals itself? Okay, e to the x. But also it's the case that any constant times e to the x. And I will just say this is the general function whose derivative equals itself. So I like this example because well, we can just think about the answer through reasoning, but also it leads us to what we will talk about next. So thank you so much, students.